Good day and welcome back. Today we're going to talk about the self-inductance and the energy stored in an inductor. At the end of this video, you should be able to explain the phenomenon of the self-inductance and also the formula regarding the self-inductance, and we're going to use it to derive the self-inductance of a solenoid. And then lastly, we're going to learn about the formula of the energy stored in an inductor. An inductor is something like the solenoid you have learned before. When we connect the inductor with a voltage source and a switch, self-inductance is a phenomenon in which the back EMF is induced in the inductor when there's change in current flowing in the inductor. The change in current only happens when we close or when we open the switch in the circuit. Let's say we close the switch in this circuit, so there will be current flow from the voltage source to the inductor. The presence of the inductor doesn't allow current to increase instantaneously. When the current starts to flow in the circuit, it also produces the magnetic field that links to the inductor. According to the Faraday's law, when there is change in magnetic flux linkage, there will be an induced EMF, which is the back EMF that induced in the inductor in this case. So there will be a current flowing from the back EMF to oppose the current flowing in the circuit. So this is why the current from the voltage source doesn't increase instantaneously, but increasing over a certain period. The induced EMF E is opposite to the voltage source, so the value of the E is negative when the current I is increasing in the circuit. So after a certain period, the current I will reach a constant value where the back EMF also becomes zero since there is no more change in the current flow and no change in the magnetic flux linkage. Next is when the switch is open. Normally the current would reduce to zero instantaneously. However, the presence of the inductor doesn't allow it to happen due to the reduction in current flow. So there is back EMF induced in the inductor, which is the same direction as the voltage source, that it provides a current flowing in the same directions to oppose the decay in current. But after a very short time, the current still reduced to zero and the induced EMF also turns to zero. In short, there is induced EMF in the inductor to oppose the rate of change in inductor. When the current is increasing in the circuit, there is an induced EMF in the inductor trying to reduce the current flow in the circuit. When it is in steady current state, when we close the switch, so there will be an induced EMF in the inductor to prevent the decays in the current. You are given with the formula of the E equal to negative L di dt. So now we're going to derive the formula of the self-inductance of a solenoid. From Faraday's law, we have learned about the induced EMF is equal to the negative of rate of change of flux. So equate both formula, we have the equations of L di dt equal to d phi dt, and then we have the Li equal to phi. In 17.1, we have learned about the phi is equal to NBA, and then we also learned about the flux density inside a solenoid is equal to mu naught Ni in chapter 16. So we substitute the formula into the equations, and then we also substitute the N with the number of turns per length. So in the end, we have the self-inductance is equal to mu naught N square A divided by the length of the solenoid. So last but not least, you are given with the formula of the energy stored in an inductor. So the energy stored in an inductor is equal to half Li squared. So you are not required to understand the derivations of this formula. Before we end this video, let us try one past year questions to summarize what we have learned in this video. So you are given with an inductor of length 0.2 meter, 200 turns, cross-sectional area of 2.5 multiplied 10 to the power negative 4 meters squared. When there's a current of 1.2 ampere flowing in the inductor, so what will be the energy stored in the inductor? So you have learned about the energy is equal to half Li squared. And then you also learn to derive the self-inductance is equal to mu naught N square A over L. So you can combine these two formulas to solve these questions. Then you substitute the formula of the self-inductance into the formula of the energy. So put in all the value, you should obtain the answer as 4.52 multiplied 10 to the power negative 5 joule. So that's conclude my discussion for today. If you have any questions, you can leave it in the comment section below. Also do leave a like, share my video and subscribe my channel. I'll see you in my next video. Thank you.